In today's video, I'll be giving you an idea of how the 2025 WAEC Physics practical, the optics question, how it's going to be asked. So this video is based on the information about the apparatus you should be expecting. So let's start off with the apparatus. You'll be given the following: a rectangular glass prism, a plane mirror, a meter rule, some drawing papers, a drawing board, 4 optical pins, and a protractor. So these are the apparatus you should be expecting. So the next question is, what's the objective of this experiment? The objective is to determine the refractive index of a rectangular prism, of a rectangular glass prism. That's the objective. So let me walk you through the way the experiment is meant to proceed, and let me give you other ideas about the experiment. So let's take a look. Let's take a look at how to carry out the experiment using the Marvin Orb Physics Lab. So this experiment is similar to one of the experiments under optics. If you go to optics and you click on experiment 8, you'll see that what we have here is very similar to what you should be expecting on the day of the exam. Okay, so let me just start off with the basics. So the objective, as I said earlier, is to determine the refractive index of a rectangular glass prism using both the laws of refraction and the laws of reflection. So this is the diagram. This is how the setup is meant to be. So you have your block prism. That's this prism. Then at the back of the rectangular glass prism, you'll be expected to place a plane mirror. Then the way it's set up is you are going to measure angle I. So this I is the angle of incidence, right? So you measure this angle I, then you draw a line, this red line, then you position 2 pins here. Then the next thing you do is to set up the glass prism and the plane mirror, then look through this other side of the glass prism, this side where you have the eyes. And once you look through it, the goal of what you're trying to achieve is to get a pin positioned in such a way that the pin is directly above any of these 2 pins. But basically, by the time you get the right alignment, these 2 should be covering themselves. So what that means is by the time you must have gotten the right spot, these 2 should be right behind themselves. This blue pin should be behind the yellow pin. And once you get that right angle, you position this pin, which is the green pin, right at that point. Then you do the same thing for pin 4. Once you've gotten that done, you link up pins 3 and 4 to touch this point on the rectangular glass prism. And once you've done that, you draw this line, which is the normal to this block prism. Once you've gotten this normal done, you measure angle E, right? You measure angle E. But typically, if you've done this correctly, this angle I should be the same as this angle E. Basically, they should be the same, right? But just carry it out. But if they are not the same, if they are far apart, that means you must have done something wrong. So you just retake it. Okay, so the next is to measure the distance between these 2 points, between O1 and O2. So this point where it touches this normal is O1. And this other point where the emergence ray comes out from is O2. So the distance between them is D. Then another thing you have to measure is theta, which is this angle here, the angle at this point, Q. So that's theta. So the next thing you'll be expected to measure is W, which is the width of this rectangular glass prism. So these are the key information you are meant to take note of. Although the W is a fixed number, so it's fixed, but the rest might change as you change the value of I. So W is fixed, but what is not fixed is this I. So once you change the value, so let's imagine the first I is 10 degrees. Then you're going to measure theta, you're going to measure D, you're going to measure E. Then the next is to change this to, let's say, 20. Then you measure theta, D, and E. then you do for all the eyes. But W will always be fixed since the width of the rectangular prism is fixed. So this is basically how you carry out the experiment. So it's straightforward, but the only thing you need to take note of is the way you determine this line where this pin is directly positioned at where this P1 and P2 are. Okay, so let's scroll down. So these are, just to recap, these are the apparatus, and the procedures, the detailed procedures are here. So if you want to go through them, but I just described them verbally, which is exactly what you have here. So, but the next question is, what do we now tabulate? Now that we've recorded theta, E, and D, what do we calculate? We calculate M, which is sine E. Then we calculate N, which is D cos theta over 2. There's a mistake here. D should be part of this. So it is D times cos theta over 2. Then repeat the procedure for other values of I and plots a graph of M on the vertical axis and N on the horizontal axis. Once that's done, we are meant to determine the slope of the graph and evaluate Q, which is 2WS. So W is the width of the rectangular prism, S is the slope. So this is what you should be expecting on the exam day. There may be slight variation to this, but this is just roughly what you should be expecting. Okay, so the next thing is the principle. So the principle is, what's the guiding formula behind this experiment? So imagine you are to write a formula that represents M as a function of N. What would that formula be? So this is what this guiding principle does. So it shows you, so this explains exactly how M and N are related, because you are plotting M against N. So there's a function or an equation that connects M and N. So the basic idea is around geometry and Snell's law and some principles around reflection. So at the end of this derivation, the final formula is this. So this is the final formula, which is M as a function of N. So this is it. M is equal to the refractive index from air to glass divided by 2 times the width of the glass times N. So what this means is the slope of this equation is the refractive index divided by 2W, which is this. So if the slope is this, if I want to calculate the refractive index, I'll just multiply slope by this. So basically 2WS is equal to the refractive index of the glass. So if you calculate your slope and you multiply by this value, you are going to get the refractive index of the glass. Okay, so that's basically how the experiment goes. Then what this graph also tells us is the y-intercept is 0. So what that means is the graph is meant to pass through the origin, or it's expected to go through the origin or very close to the origin. But in a perfect scenario, your graph should go through the origin. The y-intercept is 0, basically. Okay, so let's talk about how to actually simulate the experiment. So I'm going to use the software to simulate the experiment and to show you how it works, basically. Then we'll go through the graphing and we'll also answer some questions. So let's get into it. But if you already have the Marvin Physics Lab, you can also explore the settings where you can change the way the values of I. In other words, do you want the I to be 10, 20, 30, 40, 50? So this setting says the minimum is 10, the maximum is 50, and the step is 10. So which means we'll see values of 10, 20, 30, 40, 50. If you want to change the step maybe to 5, you can change it. If you want to change the maximum, you can also change it. Then you also have the choice to change the width of the prism. So by default, the width is 5 centimeters. Then you can also change the refractive index of the glass based on the property of the glass. If it's a Pyrex glass or plate glass or crown glass, these are the known refractive indices. But this is just the software. So the software has to work with some parameters. So you can change it to get different results if you wish to. So let's go back to the setup and let's start this simulation. Okay, So what I'm going to do now is to go to the reading. So the first setting is when I is 10, then we are meant to measure D, theta, E, and N, then N. Okay, so what I'm going to do is to change this I to 10. So which is the angle of incidence. Then I'm going to switch to this I radio button. Then what I'm going to do is to adjust this until the yellow and the blue pins are aligned. So that's basically what I'm going to do. So I'm going to adjust until that is achieved. So these are estimates of what I've gotten. So what I'm going to do is to make the measurements. So to measure, you just look at the distance between O1 and O2, which is this distance. So for what I have here, this is 1, 2, 3, 4, 5, 6. So this is about 6. So what I'm going to do here is to say my D is 6. Then what about the theta? The value of the theta is this angle. So if you have this protractor here, so this is what the theta is measuring. Is measuring, this is 5, then this is somewhere around this 10, somewhere like 11, about 11 or 12. So that's what this value is giving. It's about 11 or 12, but let's say 12.5. So let's say about 12. So this is 12. Then what about E? So E is this angle here from the normal here to this red line. So if you use a protractor, you're able to get it here. So which is 10. So as I said earlier, the angle of incidence should be the same as the angle of emergence, which is the I, and this E should be the same. Okay, then what about the M? M is sine E, which is sine 10, and that will give us 0.017. So let's say 174. Then we have N. So the value of N is D cos theta over 2, which is roughly 1.3. Okay, so we will do the same thing for when I is 20. So for when I is 20, what I'm going to do is to go back to this I and move it to 20. Then once you have 20, you go back to the I and adjust until you get the right angle. So I'm going to quickly rush through this, and once I'm done filling all the readings, we'll get back to our graph and questions. So I've completed the table of reading. There's something I needed to take note of. I noticed an error with this first reading. Initially, I wrote 6, but I had to check. I realized that it was a big mistake on my side. I didn't read the data very well, and the actual data is about 1.3 based on this meter rule, and that correction has been made, and it's also reflected on M. I also edited this. There was a slight mistake here, and everything is good. Okay, so this is the complete reading based on this triangular prism and based on the width of the, based on the rectangular prism rather, and based on the width of the rectangular prism. Okay, but if you have a different refractive index, if you have a different rectangular width, the reading might change. So now let's talk about the graph. So how do you go about plotting the graph? You start with the title. So in this case, I'm plotting M against N. Then what about the x-axis? The label is N. What about the y-axis is M? Okay, what about the range? The range is determined by the range of values that you have here. So if you want to know how to get the perfect or the ideal range, check out our video on how to make a good plot. But based on what I have here, the range is, the maximum is 5.7, the minimum is 1.3. So you want to have a range that contains all those values with extra spacing on the left and right. So I'm going to go with -1 and a maximum of 7 with a step of 1. So for the y-axis, the same thing, you check the minimum and the maximum. In this case, the minimum is 0.17, the maximum is 0.77. So you want to pick a range that's within that. So in this case, I'm going to go for, let's say, -0.2, then the maximum should be, let's say, 1. Then let's say a step of 0.2. Okay, so let's start the plotting. To plot, plotting is just all about you identifying the x and y values on this graph, then connecting the points. So if you have a real graph paper, you just mark all the points where x is, where the n is 1.3, which is on the x-axis, y is 0.17. So you identify and you keep crossing. Or if I'm going to use the software to plot the graph, I'm going to click on this graph points, this pencil sign. Then it will activate that ability to start marking my points. So when n is 1.3, which is somewhere here, which is somewhere around here, right? Then the value of y, which is the n, is 0.17. So which is 0.17 is somewhere here. So which is this, let's see. Yeah, so it's somewhere here. I'm going to click. Then when n is 2.57, so this is the middle, which is 2.5. Then 5.7 should be somewhere close to this side, right? You can easily know because if this is a division of 5, it means this is 0.25. I mean, this is, if you divide 1 by 5, right? So you're going to get 0.2. So this is like 2.2, 2.4, 2.6, 2.8, and so on. So here you see that this is 2.5, then 7 should be closer. This is 2.6, then 7 should be right at the middle because this is 2.8. So this would be 2.7. I mean 2.7, but we are targeting 5.7, not 2.7. So 5.7 will be 5, 6, so in between this. Okay, then n is 0.3, so 0.3 will be right at the middle, then 3, 4 will be somewhere here. Okay, so it will be somewhere here, which gives us this. So the next is, so I'm going to quickly locate the rest of the points, and we'll get back to it. Okay, now that we've identified all the points on the graph, the next thing to do is to join them all. So to join them, all I'm going to do is to pick this, then I'm going to find a way to connect. So as I said earlier, this line is meant to go through the origin, so which is similar to what I have here. So make sure the line touches as many points as possible. Let me just pick this. Then the next is to define your slope. Slope is all about picking 2 points on your graph. So that's what slope is all about. So I'm going to pick these 2 points, right? So I'm going to pick these 2 points. So the next is on these 2 points, where is the x1 and x2? So x1 is this, which is 3, and the x2 is 5. Then what about the y1? The y1 is this, which is 0.4, 0.4, and the y2 is this, which is roughly 0.66, 0.66. So the difference is 0.26, and the difference here is 2. Then what about the slope? The slope of this graph is 0.13. So that's the slope of this graph. So now let's answer the question that follows. So this is the question that follows. So to calculate the refractive index, we multiply 2 by W by S. Mind you, I've already submitted this so I can see the solution. So the W is the width, as I said earlier, and in our case, the width is 6, which I noted at the beginning. Then if you multiply that with our own slope, in our slope we got 0.13, but the ideal slope in this case is 0.333, so which is very close to ours. So eventually you will get something close to 1.6. Now, the second question here is, according to the law of reflection, the angle of incidence is equal to the angle of reflection. That's according to the law of reflection. Yes, the answer is yes, because in reflection, the angle of incidence is equal to the angle of reflection equals angle of incidence equals angle of reflection, and you see that here. So the angle of incidence on the plane mirror is equal to the angle of reflection. This is a plane mirror, so the angles are the same. Okay, then the last question is, we can deduce from Snell's law that angle of incidence is equal to angle of emergence for a rectangular glass prism. So the answer is yes, because for what I told you, the angle of incidence is always equal to the angle of emergence. So that's what this question is trying to prove, that are they the same? And it's yes, based on our observation. So if you are running this software, if you are running this simulation alongside me, you can easily grade yourself and by submitting, and the software will grade your performance in every aspect. To grade your table of reading, to grade your graph. It will also look at the way you perform in your axis, the way you set your axis, and all of that. I didn't answer any of the questions, so that's why it's not graded. So this is how you expect to carry out the experiment for the 2025 optics physics practical.